Energy is the grand challenge for the next 20 years for the world and for the United States. Our wealth will be related to the cost of energy and how easily we can acquire and use it.
And as oil becomes more and more scarce, we're going to have to go to more and more difficult locations to find it.
We're going to need twice as much energy by 2050 as we're using today, and about triple that much in 2100. And so the question, of course, is where are we going to get it from?
The sun, the source of light and heat that sustains our planet. At a time of rapid development and consumption, the sun represents the alternative to a potentially dwindling supply of fossil fuel.
You know, it's pure energy, basically. So as an alternative to like gasoline, coal, burning fuels, where we're releasing CO2 in the atmosphere, we're trying to use the sun to get away from that.
Right now, solar power contributes to the Earth's energy needs in a limited way, because as of yet, it is neither affordable nor efficient enough to make a global impact. What's needed is a new design.
Imagine solar cells that you could print the way you print a newspaper on large, flexible strips of plastic that wouldn't crack or break. So it could be a building material as well as a source of energy.
There is no doubt pressure.
There's a set time limit on this. We need to be able to understand solar energy. We need to be able to build better solar devices. We need to do it very soon.
To accelerate the process, governments and universities are forming research collaborations. We're going to take a close look at a unique collaboration called ANSER.
ANSER is the Argonne Northwestern Solar Energy Research Center.
Its mission, its role is to explore the basic science of solar energy and to try to look for discoveries.
This is the story of a search for how to harness the power of the sun, a search for how to solve a growing world energy crisis. This is the search for the answer. Hello and welcome to Search for the Answer. I'm Keith Oppenheim, and we're coming to you from the campus of Northwestern University, and soon we'll be taking you to another major collaborator in this story, the United States Department of Energy's Argonne National Laboratory. It's important to know in this solar energy research group called ANSER, Northwestern is the lead educational institution, but not alone. The University of Chicago, the University of Illinois, and Yale University are also participants. And we'll explore why these tightly knit research groups can be an effective way to push science forward. But first, some science basics. Did you know on any given day, the amount of energy that falls on the Earth from the sun is many, many times the energy the entire planet consumes now or would consume in the conceivable future? But you might be wondering, if that's the case, why aren't we gathering more of that power and using it? Well, it turns out capturing solar power isn't so simple. But the ANSER team, a group of about 25 senior scientists, along with 40 graduate students and postdoctoral fellows, is working on a number of ways to do just that. Let's begin with the leader of ANSER, Northwestern's Mike Wasilewski.
I'm the director of ANSER, and basically I'm the conductor of the orchestra. It's my job really to foster the collaborations, to make the connections, to make people realize where the connections are and how to best optimize that to get the result.
Mike Wasilewski and his team members are keenly aware that solar energy itself doesn't need to be discovered, it exists. Panels are on rooftops across the globe, and the conversion of sun to power is a daily reality. The problem is, it's not economical. Silicon crystals, the core material of current solar cells, are fragile and costly. Wasilewski says a solar cell of the future has to be much cheaper, like a roll of plastic flooring you could buy at the hardware store.
What we want to do is, for the average consumer, we want to maintain that efficiency or better efficiencies and then drop the cost by about a factor of 5 at least.
But coming up with new materials or concepts that could reduce solar energy costs by more than 80% is a major challenge. In response, the scientific community tackling this problem has been moving toward team concepts, the idea where groups of researchers could make faster progress if they worked as a collaborative unit. That was how, in 2007, the ANSER Center was born.
When we first thought of putting this together, we said, yes, we have a group of experts that are collaborating some of the time, but what would happen if we could get the dream team together?
Coming up, we'll introduce members of the dream team, and we'll ask why these scientists are studying photosynthesis, the way plants convert sunlight into stored energy.
We want to understand how that charge separation occurs. Can we replicate what plants do? And then can we take it one step further and do it a little bit better than plants do?
We'll take you to Argonne National Lab, where Northwestern researchers get dressed up to make the building blocks of the future.
And what we hope to do with this structure is to enhance light absorption and photocurrent in the type of solar cell we work in.
We'll take you to Argonne's Advanced Photon Source, one of the brightest X-ray sources in the world.
What we're trying to do is understand how the existing cells work and how that will lead somebody else to be able to develop this great cell in the future.
And finally, we'll learn how architecture can be a meaningful way to resolve the conflicting requirements of the solar cell. In all, the ANSER team members face uncertainty and a race against time. But despite that, they have faith in science and in themselves as they search for the answer. Photovoltaics. That's a term often associated with solar energy research, referring simply to the idea of turning light into electrical energy. At ANSER, the Argonne Northwestern Solar Energy Research Center, you'll hear a lot about different kinds of photovoltaic cells. For instance, there are inorganic photovoltaics like these solar panels made from crystal silicon. They're not easy to manufacture and so less promising as a global energy solution. But organic photovoltaics represent the growing part of solar energy research and refer to ways to create solar cells from stuff that's both plentiful and affordable. It's a critical concept because the search for the next great solar cell is as much about economy as it is about science.
The phrase goes, earth-abundant materials. In other words, you want to use elements in your molecules and materials that are cheap elements.
So where would scientists naturally turn to better understand a method of converting light into energy with reasonable efficiency? The answer is in nature itself.
We take a lot of our inspiration from photosynthesis. Plants are the one organism that's able to harness sunlight in an efficient, cost-effective way. They do it all the time.
Mike Colvin works on a concept known as artificial photosynthesis, or how to turn light into solar fuel. That fuel could be burned to power a vehicle, or it could be stored in a battery.
One of the primary events that happens in photosynthesis is charge separation. So plants absorb light on a nice sunny day like today. Light will hit one part of the plant. It will generate a charge-separated state, and then that electron will subsequently go on to different steps. And what I'm really interested in is understanding how I can generate a charge-separated state that lives long enough that I can do something with it.
Colvin is operating a device called an electron paramagnetic resonance spectrometer. With the use of lasers and powerful magnets, Colvin can separate electrons and actually track their movement on a molecular level.
So when I've got two spins that are separated, I can use either of these two instruments to look at where those electrons are.
The key idea is to use light to get electrons moving, with the goal of understanding how to get control of the energy that's released. Problem is, electrons can be erratic.
What we're trying to do is understand how charges migrate through these materials and to try to prevent them from doing other things other than getting to where they need to be.
That discovery process underscores how ANSER is, in many ways, not just about solar energy, but a quest to understand fundamental science. Sheila Ramanan is working with a laser system that can expose a sample material to light for very, very short periods of time.
It allows us to excite a sample using femtosecond pulses on the order of 100 to 150 femtoseconds. and then observe what happens after excitation out to a nanosecond.
A femtosecond is a quadrillionth of a second, not very long. And so you could think of this experiment as sort of like using a camera with a really fast shutter speed. The idea is to get a picture of what happens to electrons immediately after they've been exposed to light.
So the more we understand about what happens when light hits the materials that we want to put into these solar cells, the more we can understand about how to better design and develop these materials and these devices.
At ANSER, some of the work on artificial photosynthesis takes place right in the chemistry lab.
We're trying to turn sunlight into something that we know how to use. In the case of solar fuels, we're trying to make it into a fuel like hydrogen or methane that we know how to burn.
Amanda Samuel and Mike Vanini are looking for ways to turn light into stored energy.
One of the big challenges is being able to take water and to split it into its components. Now the question is, can we apply our systems to actually facilitate this reaction? So the splitting of water is one of the fundamental key challenges in developing solar fuel technology.
Some of the experiments involve looking at the interaction between metal-based catalysts and dyes that absorb light energy. Again, plants and photosynthesis serve as an inspiration. But the challenge is to come up with a simpler man-made chemistry that will use light to split water and make fuel without using excessive energy.
We know how to do solar fuels catalysis, but not in a cheap enough manner to make it feasible to actually run an economy that way.
Over at the Argonne National Lab, David Teedy is also doing research on solar fuels. His group is studying the chemistry of photosynthesis and searching for a catalyst, the medium that could transform light into fuel.
The research challenge is to discover new materials that do this sunlight to fuel generation in an efficient, cost-effective manner. And that requires discovering new materials because we don't know what they are right now.
Next, we walk the hallways at Argonne and explore how this world-class science center can make all the difference in the search for the answer. Argonne National Laboratory, one of 16 national laboratories operated by the United States Department of Energy. Located in the Chicago suburbs, Argonne is an ideal collaborator with universities like Northwestern, offering the latest in research technology. That includes a giant particle accelerator known as the Advanced Photon Source. There are only 4 facilities like this in the world, and there's a reason for that. It is huge. If you walk around the perimeter, it's about 1,100 meters or 2/3 of a mile. In essence, the reason this place is so big is to understand things that are very small. This facility generates extremely bright, high-energy X-rays that help scientists understand molecular activity, a critical component to the development of solar energy.
Is the pump on? Yeah.
Andrew Stickrath and Mike Mara are busy inside the Advanced Photon Source, or APS.
So this is beamline 11 IDD.
Stickrath and Mara use the power of the APS to analyze materials. Some of those might be good at absorbing light. Others might be intermediary materials or catalysts that help produce reactions and release energy. In the end, they can actually turn their results into a movie with pictures that explain what's happening to the light-exposed molecules.
It's necessary for us to understand these photo-induced properties in order to understand both A, how these function in a solar cell and how they give, say, a specific device their properties, and also how to either modify these devices or build new devices that'll have even better efficiency than the ones before.
If this part of Argonne seems overwhelmingly high-tech, hang on, there's another that may be its match. It's called the Center for Nanoscale Materials. And it's definitely not the kind of place where you just walk into without getting properly dressed. Right now, we're in what's called the clean room, and anyone who comes in here has to wear a protective suit in an attempt to keep the smallest particle of dust or contaminants away from a sample that is tested. The goal of the research is to use nanotechnology to build and analyze structures that will lead to the next generation of photovoltaic cells. Stacy Standridge and Ricky DeMarco are, in a sense, designers. They make patterns, molecular substructures that could be the building blocks of future solar cells.
So what we're looking at is essentially a completed, fabricated structure. The features you see on the image are 300 nanometers essentially, thousands times smaller than the width of a hair.
We need to be able to make them in a highly controlled fashion and down to the nanometer scale, be able to have things have exactly the structure that we want them to have.
The challenge here is to work toward a photovoltaic cell that's good at getting light in, but also good at getting electricity out.
What we want to do is try to collect as many of the electrons as we can, and the way of doing that is by making a very thin solar cell so the electron does not have to travel very far.
It turns out creating a cell that is good at absorbing light and generating energy is one of the toughest tasks of solar research. But this team has already developed potentially breakthrough solutions. That story is coming up in the search for the answer. ANSER, the Argonne Northwestern Solar Energy Research Center, is trying to answer a tough question: how to resolve the conflicting requirements of the future solar cell, how to balance light absorption and energy generation. With a little imagination, we're going to explain the conundrum of the solar cell of the future with pizza. Hang on, this just might make sense. Okay, first think of each of these pizzas as a solar cell. One is thin and the other is thick. Now this thick pizza, it would be great at absorbing light. Trouble is, if you look inside, it's too thick for the electrons to get out. They would tend to get lost. Not so with this thin pizza. As a solar cell, the electrons would have a better chance of getting to where you want them to go, but it's not nearly as good at absorbing light. So for the ANSER team, there's always this conflict between thick and thin, getting light in and getting electricity out. The question is, can researchers design a new pizza, a new cell that can do both?
So if you used carbon disulfide or H2S, would you get FES2?
Mike Pellin is the Deputy Director of ANSER and the Director of the Materials Science Division at Argonne National Laboratory. He conducts research on dye-sensitized solar cells. These are three-dimensional structures which include a dark layer of dye molecules, ideal for absorbing light. With these cells, Pellin's team is working on new architectures that will have the advantages of both thick and thin. It's called folding.
So we've been building structures like these where we take that structure and we fold it a lot of times. And so then the light has to pass through many layers of dye, but the electron injected still has to only go through that nanometers of wide bandgap oxide to get out.
Folding is one example of a broader concept at ANSER, the idea of creating precise molecules that can be engineered to have the best properties.
So this is the chamber in which all the magic happens.
Alex Martinson, a chemist at Argonne, is operating a complex instrument, the Bennick TSF 500. This device uses a revolutionary technique called atomic layer deposition.
Atomic layer deposition works by delivering different molecular precursors in the proper sequence.
Martinson works with Jeff Elam, an Argonne chemist who explains that atomic layer deposition gives scientists exquisite control.
It allows you to make material in the form of thin films and to put them down one atomic layer at a time, and those films can be virtually any material. It can be a metal oxide or an element or a metal sulfide, and so all of these types of materials are relevant to making photovoltaics.
There is another concept cooking which involves a different way to convert the power of the sun into power we can use. Mercuri Kanatsidis studies thermoelectrics, which involves using mirrors to create intense heat, then converting that heat into electrical power.
The heat is generated, the temperature goes up, and then temperature difference applied to the thermoelectric material drives the device, and you create electricity.
Kanatsidis' research group, along with others around the world, has succeeded in significantly increasing the efficiency of experimental thermoelectric systems. He argues that, along with other types of solar power, thermoelectrics will be an important piece of the energy puzzle.
It's not going to save the world, but it could help save the world.
To help save the world, no easy task. Because as promising as all these technologies are, the scientists at ANSER know they have a long way to go. Yet they have a clear sense of mission. The mission of ANSER is to take the energy that's already shining on the Earth and convert it into a global solution.
I mean, making the world a better place, I mean, that sounds kind of lofty, but, you know, we're really trying to make a difference and affect people's lives.
The mission of ANSER is to take the best and the brightest and share ideas.
It can't be tackled by one team. You need something as large as the Argonne Northwestern Solar Energy Research Center to go after this.
The mission of ANSER is to make breakthroughs.
It's been the history of Argonne and the history of Northwestern to make discoveries. These things happen.
And yet, the mission still faces enormous obstacles. But in the search for the answer, those challenges are a reminder that the outcome of solar research could be one of the most important scientific achievements of our century.
It's world-changing, one way or another. In other words, I have a presentation I sometimes give to groups that the last slide I show is the beautiful sun above the water. And the question I always ask people, is it sunrise or is it sunset? So that's up to us to determine.